Okay, good. Yeah. So yeah, I mean, this thing came up just 2 days ago, but I think it's a comfortable topic. We can cover that. Hopefully, do justice to what he meant to cover, how he meant to present it here. So here basically I think the one point is that the theme of this presentation is now about bringing three technologies together: persistent memory, and then CXL and NVMe. So he mentions that basically here we're saying is that persistent memory we've talked about in past has been discussed here, and now we want to talk about how this can be really realized in context of CXL, and and particularly then applying computational storage to that memory paradigm, right? So you need one additional piece beyond CXL for that, and we'll talk about that. So what is CXL? So I'm pretty sure that almost everyone here has heard about this new interconnect that is being led by basically multiple companies: Intel, hyperscalers, silicon providers. Xilinx is also on the board of this consortium. And just a little bit of background for people that this desire to have additional capability added to the interconnect, as it interconnects from the host to accelerators or external devices, that's been there for now a number of years. Multiple efforts that we're trying to address that this new capability opportunity. And now the really good thing is that with CXL, that finally I think the whole ecosystem is coming together, where all the silicon vendors, system vendors, hyperscalers, everybody is basically behind the standard, and now we can truly look forward to moving forward with additional capability beyond PCIe. So what is CXL? CXL is really, it's very compatible. It just builds on top of PCIe. I think for large number of cases, PCIe really is the right framework when you're doing I/O coherent traffic between the accelerator and the host. But there are use cases that are developing where you want to bring heterogeneous architectures where the accelerator is more like closer to the processor. It can do sharing of resources with the processor. Also, the memory attached to the accelerator is now part of the system memory pool as opposed to being a private memory. So CXL really builds on top of PCIe. So here, it can connect into the PCIe connector. And the way to think about it is this: that at the discovery time, as a link comes up, right? You can, if there's a PCIe card that you have put on that slot, you'll connect to the host as a PCIe. Or if you have put a CXL capable slot, connected card, then the link trains as a CXL link. The speed is consistent with PCIe Gen 5. Is the framing format on the wire would change. It will be CXL format. It's called FLIT format for CXL. So this is how it basically builds on PCIe. So speed-wise is completely working with the PCIe there, 32 gig Gen 5 speeds, and basically with this now push for considering device attached memory to be part of system memory, which really calls for very low latency interconnect. Right, and also now with accelerator performance requirements going up, where you also could really benefit from more bandwidth. So there's a really now aggressive push to move, PCIe Gen 5 to even get to PCIe Gen 6 very quickly. So let's now look at the next level detail of basically the CXL other attributes. So it comes up as a CXL link, right, based on PCIe Gen 5. Then CXL has this memory, basically CXL has these additional capabilities beyond the PCIe. CXL has these three types of, which actually is shown in the next slide, is the three types of traffic that it can carry. Is a native PCIe traffic, which is called CXL.io. Then there is memory, where basically you are like a memory target for a point of coherence, which is in the host. So just like locally you have DIMM slots, at point of coherence beyond that you go to local memory controller. CXL allows that memory controller to also exist across the link, right? It's just, that's a simple way to view it. So point of coherence is still with the host, and then you can come and basically this is part of the memory pool. So that's .mem. In this case, there is already work done in UEFI to expose this memory differently than reserved memory. It is exposed as conventional memory, but with a special marking, which is called a specific purpose memory, SPM. So it is basically giving this guidance that ultimately it is part of system memory. However, it is not necessarily suitable for OS to allocate its own data structures here, right? And there may be additional restrictions that may apply. But it's a paged, it can be a paged memory also, but it is also, you can have the shared page tables with the host and so on and so forth, right? It depends on how far on the OS layers we go to expose this, but it is really a memory that is part of essentially, you can say either driver managed within the OS or kernel managed itself. Okay. So this is .mem, and this memory can be hot plugged, right? Because it's connecting to a device, it is more suitable to be hot pluggable memory. Then, from the form factor point of view, the standard PCIe form factors would work. Also, there is active work that is underway, that's happening, that today you have this even.s form factor or U2 form factors where they can also connect over essentially PCIe. So it would apply there as well. So then from management perspective, so because CXL also supports this PCIe traffic, and essentially PCI, it completely supports the PCI management framework. So all the configuration, discovery, so the device is discovered as a PCIe device, then you determine that also this is CXL capable, and then you get additional capabilities visible to you at this point in time. But the management wise, it is otherwise essentially consistent with the PCIe. And then the other frameworks also are available where basically if you have some support for SM bus, that would just come naturally with this as well. And in the OS from management perspective, again this other ACPI framework, and also the other dimensions here like HMAT tables, which are really giving you this description of a different nodes and how far apart the memory nodes are from the compute nodes and so on and so forth. This will just show up as part of you can consider as a NUMA socket essentially in that framework. Now this is getting into those things that I had to mention already. There is that there are really three types of traffic that is carried over CXL, CXL.io, which is for discovery configuration, and also address translation service happens over this. And because your caches here, you want to enable cache access to be done from virtual address space, and then but caches are physically addressed. Basically, as part of .cache of CXL, you have to support address translation service. So that is also part of basically you ride over CXL.io for ATS support. Interrupts, MSI, signaling you leverage from the IO framework. CXL.cache is really now, today for PCIe, the accelerators or any functions on the PCIe device, the coherency paradigm that they use is what's called IO coherency, which is basically they can do any access to the host memory. They will get the latest copy from wherever it is, whichever cache holds that latest copy, but the device cannot cache the data for itself. If it needs to reuse the data, it has to go to the host again, or it has to just make a local copy which is not coherent with the host, and then use a data sharing paradigm which can deal with existence of non-coherent data. So you basically, there are certain paradigms there where you explicitly move the data around. As you consume the data, you make a local copy, and then when you produce the data, you push it back to the host, right? A producer-consumer model where coherency can be managed at the point of transitions. So, but in case of CXL.cache, what you get is that now you can actually cache the accesses that you're doing to the host, and for future accesses you do not have to go back to the host, and basically the coherency is maintained. If the host needs that line of data, you will get the snoops. So this is a .cache. .memory is really, as talked about, it's like a memory controller attached across the device. Still controlled by the point of coherence in the host. There is one other detail quickly here, is that the local memory is a little bit more than just the local memory as a memory controller. Now there's a level of detail. There is a support in CXL that allows you to go to this memory directly, because if I have an accelerator and memory on the same device, this is a type 2 device in the CXL, so in that case it doesn't really make sense to go to the host, get the data from local memory, right, go and make a hairpin turns like this. So there is a provision in CXL that at certain, inconsistent to the producer consumer model, you can essentially have support where you can still maintain coherency, right, when you can directly go to the memory that is local to you, but this is not for fine-grained data sharing. It is more for producer consumer model, coarse-grained data sharing, but the coherency is still maintained through hardware mechanisms. Okay, so this is some detail there that is available in the spec. So these are three basically types of capabilities that CXL is adding. Now what can, so again, in terms of the .io is doing DMA, interrupts, we talked about SRAOV support is there, ATS, we talked about that already. And then of course you get NVMe interfaces as well, because that's a PCIe interface. .mem, we talked about that already here. And here, I mean, the memory could be a persistent memory, that's what's more interesting here, but could be just general purpose memory as well, so DDR memory as well. .cache is able to cache. How am I doing with time? I think I'm taking two. Is okay?
12, 15 minutes, yeah.
Okay, so I have to pass on to, okay, so sounds great, okay. So representative use cases. Now what are the new use cases that you can do with CXL? So first look at the case when it's a .cache. So it's like flipped, you can think host on the bottom and the device on the top, host on the top, device on the bottom, or it's just the other way around here. So now let's think what you can do with this. That first of all, you can do, in a NIC today, right? NIC wants to really work on the headers, right? It wants to do the header processing, and then it wants to pass on the payload to the host. In this case, instead of now buffering the data locally in the NIC, where you need to have additional memory, right, a DDR attached, you can really pass on the data to the host as soon as you can, and if you need to do further processing, you can still keep the cached copy of what is important to you in your cache and operate on it without having to go. Basically passing the packet, or as soon as you can pass on the packet to the host, does not mean that you cannot work on it efficiently. You can still keep the portions that are interesting to you, they'll come to you, stay in the cache, and you can operate on it, right? So it allows you to optimize the memory that you need to connect to the NIC. And the second thing is that the atomics now becomes a lot more efficient to implement, essentially, atomic operations. You don't have to just go all the time remote atomics to the host, you can do the atomics locally, right, in the memory. So that's the second benefit. And protocols wise, so in this case, subset of the PCI that is a CXL that is supported for this case is CXL.io and CXL.cache. Now let's look at the memory case when I have a cache, but I also have some local memory. This is the case I talked about already earlier. In this case, accelerator could be a GPU, right? Or you could be doing some computation near memory. Here, if the paradigm is still producer-consumer paradigm, right? What you can do is you have an accelerator, you have memory, you can work on this memory, but this memory is not private anymore. But from performance perspective, you still get the goodness of it being private, as if it were private, because it's local to you. But at the same time, you don't have to do this burden of explicitly copying your produced results back to the host, right? So you're a producer of the data, you just produce it here. As long as the latency attributes are correct, right? Overall, it's a win, right? And that's where the push is to have a low latency interconnect, so that this works out really well. And then memory buffers, where basically you have simple just memory expansion, but no processing being done on the device. Then you get a combination of CXL.io with CXL.mem. So these are different types of configurations you get. Okay.
Persistent memory would likely be
in that category, yes. That's a good point, yes, absolutely. Starting will be really there for persistent memory. So more simple paradigm, and there's active work in that space from software enablement perspective that we are covering here already. So I'm going to now basically pass down to you. Yeah.
So when you have a guy that doesn't show up, who has no hair and likes to swear, what do? You bring a guy who does storage, has hair, and doesn't like to swear. It's the best way to it's the best way to give and take. So I am not an NVDIMM guy, but I love NVDIMM technology, so we can certainly talk to it. And when you look at it from this perspective, the idea behind CXL, what it's bringing to the market, and how in the next slide you'll see it's valid for me to be standing up here, is that the PCIe Transport's a perfect solution for a lot of what we're doing. We're looking at how NVDIMMs are being manipulated and used in different ways. The persistent memory space is growing. We're seeing a lot of opportunity to use things like CXL and these different protocols with the CXL.io and .mem. And when you talk about it from this perspective, we put a DMA engine in the memory buffer. We have that opportunity to do all this over PCIe with CXL. So what do we do now that we've had all these cool ideas? We keep thinking about storage, compute, and memory all in their independent functions and features. Let's have some fun and now throw the compute concept into it. So this is where the idea of computational storage comes into play. So computational storage is one of the working groups within SNIA. I happen to be the chair of that group, a la why I'm up on stage. And we see the value in bringing this concept of computational storage, which includes the idea of a processor using persistent memory, which is what Stephen Bates' company is actually working on today, and using CXL-based NVDIMMs plus persistent memory and these acceleration capabilities that are provided through the computational storage working group efforts. So you have a controller that now has compute capability in it. In the case of Iditacom, it's an FPGA. In the case of NGD Systems, it's an ASIC, but we've added compute resources into the controller that is managing some form of persistent memory, non-volatile memory, or other resources, and it's utilizing the NVMe and CXL partnership to accomplish those tasks. And that's really what we're kind of after. So computation on persistent memory in a CXL device is a great way to do that, and that's all being worked together throughout the synergies of the standards body's work between CXL, SNIA, NVMe. So it's this concept, as it was shown on the front page, is this idea of a trifecta. So some ideas here are talking about storage-centric computation. So there's examples that have been highlighted in the use of being able to do compression offload, analytics with AI and ML. These are all different use cases that can be done using NVMe, CXL, persistent memory, and storage products all in synergy together in systems, where we're starting to pull these pieces and instead of just keeping it as a singular order of I have compute, I have memory, and I have storage, and we're starting to look at them as three independent parts that can be intermingled in ways that we've never thought of before. So instead of an inline process of going through the compute to memory to storage and back, we can go to compute straight to storage, or we can go compute to memory and memory straight to storage, and those types of things. And that's where this concept of overlapping these abilities and doing things like true DMA and other integrations of these efforts. A good example is with peer-to-peer and the CMB. Those are features that have been brought up to us by NVMe that can also be leveraged with this technology. So bringing these together is a benefit to the industry. It helps us all understand that there are new and innovative ways to look at things and be able to drive forward using a common, thank you, sir, a common interface like NVMe, PCIe, CXL, bring it all together, but at the same time make sure that it's easy for all of you who are developers to deploy these solutions, because we don't want to make it too difficult. It's all about the KISS principle, keep it simple, stupid. And so how does that affect what we're doing here in this particular space? This is the call to action. But before we get too much into this slide, we have to have a moment of silence. This will be the last time you will hear the definition of the solid state storage initiative, because you see there's this wonderful thing called an initiative. It's the marketing arm of getting the working group guys to get together. And it's reached its fruitful limits with things like CXL, computational storage, persistent memory, all being managed by the initiative. SSSI officially dies today. So, moment of silence. What we're going to call it, that's a good question. The phoenix has yet to rise from the ashes. We have some ideas. So if you have an idea on what you would call an initiative that supports persistent memory, storage, computational storage, and or CXL and other interfaces, Marty's sitting right up here. She'd gladly take your ideas on suggestions for the new name. Meanwhile,
drink at the reception.
or buy our free drink at the reception. So there is work being done from a computational storage perspective. We've joined the initiative along with the persistent memory teams. We're working cohesively as an organization to bring this together. We have representatives from NVMe, from CXL, all of it putting the efforts to make sure that whatever you need to deploy these technologies is provided to you in such a way that it's easy to put into practice. So there's liaison agreements between all of these different organizations, and we welcome you to join whatever we are going to call ourselves, or the to be named. So we could put up a symbol of Prince and say, formerly called Prince or something, but formerly known as, yes. So at the end of the day, CXL is very valuable to the market. It's the first open interface and protocol that's being driven by everybody that's of significance in the market from a compute perspective. Intel, AMD, ARM, all of those guys, IBM, have all gotten together and said, you know what, we agree, it's time for some change, some proactive, productive change, and we're going to make that happen. We have the different ways of integrating it, so we've thought through the different process patterns. It's not just a one-time thing. We're not going to do a version of it. How can we use this in the most meaningful way? So you get your CXL.io, you get your CXL.mem, and your .cache. At the end of the day, you've got the ability to put this trifecta together. I would call it the fourth pillar of that. So three-legged stools are great, four-legged stools are even better. So since I'm a storage guy, I'll say that we could add storage into this as well, because there's opportunity to create storage devices that talk meaningfully over this process and this capability just as much as the persistent memory and the other aspects of these protocols. So CXL is definitely here to stay. We're very excited about it, even from like I said, from a storage perspective. It's a perfect solution to help drive forward the persistent development of persistent memory solutions, whether it be through NVDIMM, computational storage, or other aspects of that. So hopefully this gave you a little bit of overview of what those interfaces and capabilities are. And again, we welcome you to join the efforts to help continue to drive these things forward and make them better for everybody. So.
Right. Anybody have any questions? We got time for one question, so I'm going to go back here, and you'll have to catch me after the piece.
I have two questions actually. So the quick one would be. Okay, so I'll just. So on the persistent memory, the solutions are actually adding that TBs of persistent memory right at the host. So what are the applications which will use a memory or CXL.memory by using a memory which is attached to the accelerator? What applications will spill over the terabytes of memories and try to use the memory inside an accelerator?
I think from my perspective, I don't have a good enough answer to solve that problem for you. We can certainly follow up and get you some answers. I think Jim is ready to hop in and give some feedback.
Let me jump in on this one. It's important, and maybe didn't come through really clear. You should expect that persistent memory will be moving off of the DDR bus. It's not the best place for persistent memory. Today, it's the only place that persistent memory could be put. And instead, and as I said this morning, not all of you were here, there's, it's a perfect example is the more persistent memory you have in the system, you would want more DRAM as well. But the way, if you're putting it on the DDR bus, as you put more persistent memory, DRAM goes down. In fact, you're trading them off. So by moving persistent memory off onto CXL on its own, you could have the limitations we have now, where we talked about 6 terabytes of memory on a dual processor system. We'll laugh at that someday in the future, because you'll be able to have it'll be like the 127 kilobytes of memory is what you get on a PC. This is changing. So don't think of what kind of applications are going to spill over beyond what's on the DDR bus.
Yeah.
Persistent memory will really be out there. And there's been a lot of criticism on all of this, because The techniques being used aren't completely open. CXL was designed so that everything you need to do in order to implement persistent memory, all the flushes and all that type of information is all designed into CXL in an industry standard format. So it's a big deal.
Yeah. So
Did you just cough in my microphone, by the way?
There you go. So at the end of the day, to his point, it's not about filling DRAM slots anymore. It's about where can I attach this device using the PCIe protocol. We've got chassis now that hold 24 or more, 4800 plus PCIe attached devices. Those can be storage, those can be CXL based persistent memory, they can be all of those solutions. So again, it's disaggregating all of that into a way that we can now compose it in ways we've never thought of before.
Yeah, and I got to say, one of my favorite things that I used to say from my industry experience was the easiest way to implement software on a new piece of hardware is put that hardware on a programmer's desk and say, oh yeah, your software doesn't work. Usually works within about a month. All right, we got